Hey, is it okay with the microphone from home?
Sì, prof, si sente.
Okay, so let's again go back to where we were, and so let's load a couple of pictures. So if you remember, we started here. So let's actually do like this. And again, so the topic of today's lesson is again rigid body kinematics. Okay, so last time we ended the lesson saying that in order to be able to describe the rotation and the translation, so the general motion of a rigid body, we needed to define 6 parameters in order to be able to detect in a unique way the position and the orientation of the body. So we also said that to ease this task, we were intended to define a frame for each rigid body. So each body is basically has a two-way unique connection with its own rigid body. Okay, so there is basically no distinction possible between the frame of the rigid body and the rigid body itself. It's basically talking about one is actually talking about the other because there is no relative motion. All of this is inserted within the 3D space, the 3D Eulerian space, which is referred to thanks to resorting to an inertial frame, which we call x1, x2, and x3. Okay, so it's again a 3D right-handed Cartesian frame. The same goes for the local body frame, which is as well a Cartesian frame. And then we said that the general motion can be thought of as a translation and plus a rotation. So the rotation of the body, the translation of the body equals to the translation between the two reference frames, the inertial one, which is fixed in space, and the one which is attached to the body, which is called again local frame. And in this sense, we can identify this translation through a vector, which basically indicates the relative position between the origins of the local frame and the inertial frame. In particular, we have that this vector R indicates the position of the origin of the local frame with respect to the inertial frame. Okay? So these are already 3 parameters, because the vector has 3 components in the 3D Eulerian space. So in this case, we can, for example, say that the position of a point, which we call P0, in the body can be identified as a vector which we can call R0. Now, in this sense, we can say that for this, let's say, case A, we have that the position in space of point P0, okay? So I want to be clear on this. There is a difference between Lagrangian and Eulerian description of motion, as you know, because the Lagrangian one is based on referring always to the same portion of the body, okay? And you follow it, okay, wherever it goes. This is one thing. The other one is the Eulerian description. In the Eulerian description, you only matter about the position in the 3D space, which is typically Eulerian, and that's why it's called Eulerian description, okay? So now we are referring always to the same portion of the body, and with respect to that portion, which will translate and rotate together with the body, we are indicating its position in the space, okay? So P0 is the position in the 3D space. To indicate the position of the in the 3D space of this point, of this portion of the body, we can therefore call it, for example, P. This is not capital case, it's small case. Small case P, it's a vector, which in the first case is just R0, sorry, R, capital R, plus R0 with no overbar. Okay, so please again note that I'm not putting any overbar right now. In this case, so R0 is this vector which goes from O prime, which is the origin of the local frame, to P0. And it is expressed with respect to the inertial frame. So its coordinates are basically the projection of R0 with respect to x1, x2, and x3. Okay? All right. But again, if we put ourselves on the local frame, we can as well describe the position of point P0 of the portion of the body which occupies the position P0 with respect to O prime. Okay? We see nothing else because we are completely immersed in the local frame. And in this case, we can define a vector, sorry, which we usually refer to as R0 over bar, R0 over bar. Since without any loss of generality, in this case one, we only are taking into account translation, and we say that initially the local frame and the inertial frame are co-oriented, no? So they are parallel. We can say that during this motion, which is a pure translation, R0 is equal to R0 over bar. They are exactly the same thing, because projecting R0 over x1, x2, x3, or over B1, B2, and B3 is basically just the same. The components are just the same. So there is no difference, except, let's say, in terms of practical components between R0 and R0 over bar. But there is a conceptual difference, okay? And this conceptual difference arises when you take into account a rotation as well, okay? So here, just to conclude what I was saying, you can, without any kind of problem, say that this is also valid, okay, in the first case, just in the first case. Because, as I said, we started saying that the two frames were parallel, and then let's say the following motion is just a pure translation. So no issues. But then let's take a look at case 2 here. Case 2, you have, let's say, a more general motion composed of a translation and a rotation. So now, if I again refer to the same portion of the body, it will no longer occupy point P0 in the 3D space, but it will occupy another point which we can call P, capital P. Okay? So please do not confuse the name of points, which is typically done with capital letters, with small letters, with an underbar, which we use as a way of notifying vectors. Okay? Typically, vectors have an underbar. Okay? All right. So in this case, we call this still R0. Okay? In our way of calling it. So R0 is still a vector which lives in the 3D space. Okay? And as its components refer to the inertial frame. Okay? Of course, now R0 is not anymore R0 of before. Okay? But we call it the same way. Now, if we refer to R0 over bar, can we say that the two are the same? No. Why? Because if we take into account this vector, O prime P, and we project it over x1, x2, and x3, we have the components of the vector R0 without an overbar. But if we project it over B1, B2, and B3, the results will be the same. And so the components will be the same. The different. And so that's why we can't say anymore that R0 and R0 overbar are the same. All right. So in general, when we have, let's say, a rotation involved, and we do not make the assumption of having the frames, the local and the inertial one, which are initially parallel, we can't confuse R0 and R0 overbar. Okay? But okay, so now the question follows natural, because in the second case we have the P, so the position of, let's say, of the vector P in this case. So this was of P0. Now it's of point P. okay, is R0 plus what? R0 without an overbar, again. But what if I want to describe this position, again, making reference to quantities which are expressed in the local frame? Well, as we will see, we will be able to write R0, okay, plus a delta R. Okay, why? Because this delta R is basically, can be thought of as, if we think that P0 was here, okay, before, now we are moving here, okay? So this is my delta R. Okay, is this correct? Let's look at it with a drawing, which hopefully will clarify things. So you see, this is exactly what we were saying. So we were saying that point P, sorry, the position P of the point P, capital P, is equal to R, as we were saying here in the left, plus, we said R0, and this, we wanted to rewrite it as R, capital R, R0 over bar plus delta R. You see? So here, basically, first we were in P0. Now we move to P as an effect of the rotation. And this vector going from P0 to P is what we call delta R. You see, so this is basically just a zoom. Is a zoom view. Okay? So why am I actually, let's say, describing all these change in position, introducing angles? Because eventually, let's say my object, as I was introducing you before, is to be able to describe the new position of points, so P, referring only to quantities which live in the local frame. As we will see, this is super useful, okay, in the development of the formulation, okay? But again, this is not yet done. Actually, we just started. So, as I said, we can think of this change of position from point P0 to point P of my portion of the body as the effect of a rotation of the body about an axis of rotation which we identify through a vector, a unit vector V. Okay? So, of what? Of an angle theta. Okay? So you see that we go from P0 to P as an effect of a rotation. Sorry. Well, that's the point of. Okay, sorry. That's a little bit of. Oops, I didn't remember that we had this drawback using PDF. We can redo like this. Okay? So just allow me to rewrite. So this is a zoom. And this, you see, going from P0 to P, is basically, you can describe this motion as a rotation about the axis O prime C, which is basically completely defined by the unit vector V. So P0, it moves about the axis O prime C and goes from P0 to P, okay, of describing the angle theta. All right? Okay. And as we said, P0 to P is basically here, delta R. So from this picture, from this zoom view, you can see that delta R can be thought of as the sum of two contributes. So of vectors A1 plus vector A2, which are orthogonal the one respect to the other. You see, we go from P0 A2 and then A1. So if we want to describe this delta 0 a little bit more in detail, into details, we have to describe this A1 and A2. All right, let's see how we can do this. So let's start with A1. Let's start with the module of A1. So it's somehow its intensity, which we will denote like this. So A1 can be described as what? Well, A1 is A, which is nothing different than the radius of this circle, describing by point P0, going from P0 to P. So it's A. A in this zoom view is CP. This triangle P0, PC, of course, is such that P0, C, and CP are equal, and they are A, of course, right? They are the radius of the circumference. Now, so A1 is nothing different than A times what? Sinus of theta. Well, it's very apparent, no? But now, what is it? A. How can we actually rewrite A? A, which is CP or CP0, they are the same, can be thought of as R0, R0, times the sinus of alpha. Can you see it from the drawing? Because here we have a 90-degree angle, so we have that. This is R0, sinus of alpha, in which we have to remember that O prime C P0 is a 90-degree angle. Okay, the way we have actually described it. So this is the first thing. And so basically you can rewrite, instead of R of A, this part here. Then we can write the following. Which
angle is alpha?
Alpha is this angle here. Is the one between. Yeah, here there is a little bit of there is a little bit of mistake. So alpha is actually the one going from C O prime P0. So it's this one. Sorry, it's this one here. It's here. This is alpha. Sorry for the mistake. So we can try to. This is alpha. It's the angle included between R0 over bar and the axis of rotation. Okay? I will correct that also in the notes. Okay.
But there's a difference between what we said. So P initially was R over bar.
Sorry, come again?
The second case, P was actually R over bar.
And
here P0 is R over bar.
No. P is R without an overbar. In the first case, P0 could be identified as without any kind of loss of difference of generality between R0 and R0 overbar. They were the same because the two frames were completely aligned. So we choose R0 overbar. Then in the second case, we couldn't use without any difference the two notations, and we had to refer to R0 without an overbar. That's why we call it like this here. Okay. All right. So if we go on, we can write that A1 from here we have that A is, as we said, R0 sinus of alpha. But do you know what can be expressed like this? When you have the operation between two vectors, which includes the sinus of the angles included between them, is the vector product, right? The product between two vectors is the modulo of the first times the modulo of the second times the sinus of the angles which is included. So this is what? V. Remember that V is a unit vector. Okay, so the modulo of V is basically nothing. Okay, times R0 times the sinus of alpha, and therefore this can be written as V vector R0 over bar. Of course, as a module. Are you okay with that? So we start from A. From the drawing, we saw that it can be expressed as R0 over bar times sinus alpha, multiplied by 1, basically, because this is the sinus of V. This is the modulo of V. V is a unit vector identifying the axis of rotation. So there is no difference, because this is 1. This is 1, so we just multiply it by 1. But this is exactly the definition of the module of the vector product. Okay, so A is the module of the vector product V times R0 over bar. All right. So if we go again a little bit more forward, and we try to use what we have just found, the vector A1 is then we saw A times sinus of theta. And then we saw that the A has basically, sorry, here we missed a part, so we cannot write it here. So this is the intensity, the modulo of the vector, but then we have to add, since here we have a vector, a direction, okay? So it has to be a vector quantity. So let's try to find out how to express this direction of the vector A1. So let's go back to the drawing. A1 is perpendicular to A2, okay? So I'm not sure if this was clear enough from the drawing, but this is a 90-degree angle. So it means that A1 is basically orthogonal to what? To the direction defined by P0 and C. Okay? So A is basically a line in this direction. Okay? It's orthogonal to P0C. You see, A1 is like this, so P0C, P0C, so A is like here. It's actually going here. But how can we express a direction which is orthogonal to the plane defined by C, P0, O prime? Again, through a vector product. Because the vector, if you think about the vector product between R0 over bar and V, it defines a direction which is orthogonal to the plane C, P0, O prime. Okay, so let's do it. So A1 has this direction. So we will define it like this. Oops, sorry. So it's V times, we said, R0 over bar. But we only want the direction. So we have to divide this by its module, right? So this now is this one here in brackets is a unit vector, right? Because again, it's a direction times divided by its module. All right, but now we remember that A, we just demonstrated that it's V times R0 over bar. Okay? So this can be simplified. And eventually, we just are left with what? With v times r0 multiplied by the sinus of theta. Okay? And this is the first result. Why did we do this? Because you see, keep in mind what is our final goal. Our final goal is to express that delta r resorting to quantities living inside the local frame. So you see, we only expressed so far a first part of that delta r, which is a1. And a1, in this case, is composed as a, let's say, an operation involving r0 over bar, sorry. So v, which is something, again, is a unit vector that describes the rotation, and then the rotation itself. Okay, so we are getting there somehow. Now we have to describe a2. To describe a2, we start again from the module. So let's have a look again at the picture. I would say that the module of a2, which is p0d, can be described as cp0 minus cd. All right? But cp0 is a, because this is a triangle which is described within a circumference. So these are the radiuses, p0c and cp. So they are equal. And cd is what? Is a times the cosinus of theta, right? So if we write this is a minus a cosinus of theta. So if we group it, it's basically 1 minus cosinus of theta times a. And if we use the renowned formula of the trigonometry, this can be written as 2a, times the square of the sinus of theta divided by 2. Okay, this is 1 minus cosinus of theta is, twice the sinus squared of theta halved. Okay, so this is, again, the intensity of the vector. Now the module. Now we have to deal with, again, with the direction. And to express the direction, let's have a look again at the drawing. So a2 is perpendicular to a1, right? We saw it here. So if the direction of a1 is v vector r0 over bar, as we saw before, if we apply again the vector product, we will get something which is orthogonal, right? So if the direction of a1 was v times r0 over bar, if we multiply it again by v, we get the direction which we need, right? So a2 as a vector is 2a sinus squared of theta divided by 2. And then, as I said, the direction. So is v times r0. Okay, so this is the orthogonal. This is just really comes straightforward from the definition of vector product. No, it's actually it must be orthogonal to the vectors which compose the two pairs. So, okay, so this is something orthogonal to v and to v times r0. So this is a1, the direction of a1. This is the direction of v. So this has to be orthogonal to v, to the plane defined by v and a1. And that's actually the direction that we need. But, yeah, sorry, correct. But this is not a unit vector, so because we need to define a direction again. So we have to divide it by its intensity. What is its intensity? Can you guess it? Well, we can rewrite exactly, let's say, the upper part of the fraction, but v doesn't add anything, right? So we can even just write v times r0 over bar. Are you with me with that? So what I'm saying is that v times r0 over bar is equal to v times r0 over bar. Is this okay with you? Well, v is a unit vector, so it doesn't really add anything in terms of intensity. But look at this. I think we have already encountered this. It's A. We have just demonstrated in the first part. This is A. Right? So, if you allow me to erase this, this can be rewritten as 2A times the sinus squared of theta divided by 2, V applied over V times R0 over bar, divided by A. Right? And this we can simplify. So that eventually we can write then 8. I will write it here just not to go to another page, so it's included everywhere. So let's do like this. So this is 2 sinus of theta divided by 2 squared multiplied by V applied over V times R0 over bar. Okay? Is this okay with you? Nice. Okay, but so with all this in mind, we can now finally express delta R, right? This was our initial scope. So our delta R, which we recall that it's A1 plus A2, is equal then to V applied over R0 times the sinus of theta plus 2. Allow me to just move this a little bit here. Sinus squared of theta divided by 2, which multiplies V applied over V times R0 over bar. Okay, so you see, we were eventually able to express these unknown weird quantities only resorting to something which lives into the local frame space, to the angle of rotation and an axis of rotation. Okay, so now we can finally answer to the initial question of expressing the position of point P as a sum of what? R plus, we said, R0 over bar plus delta R, which is, well, we're just doing a sum this here, okay? R0 plus V applied over R0 over bar sinus of theta plus 2 sinus squared of theta divided by 2, this is squared, applied over V times R0 over bar. Okay? Now we do something, let's say we introduce a notation. We say that V times R0 can be expressed introducing a skew matrix like this. So matrices will be indicated in this course as a double underbar. Okay, so it's an underbar. So this is a matrix, and typically with a tilde on top. And we will see how this is structured. So we are actually saying that we express the vector product as a matrix product between a matrix, a skew matrix V, which we will define now, always applied over R0 over bar. So where this mysterious skew matrix is defined based on, of course, on the unit vector V, like this: 0 minus V3, V2, where V1, V2, and V3 are the components, of course, of the unit vector. Then it's V3, 0, minus V1, minus V2, V1, and 0. As you see, it's a skew matrix. And I assure you that if you apply this vector, this matrix, V tilde, over R0, or you actually, let's say, do this, this vector multiplication, this vector product, you actually obtain the same vector. Okay, so it's just a notation. It's just a notation, but it will actually help us a lot. Because now our vector P, I will omit from now on the capital P below the vector P, okay? We've understood that we are actually talking about the position of point P. So our position vector can be rewritten as R, capital R, plus R0 over bar, plus, well, is, as we said, the skew matrix V tilde applied over R0 over bar times the sinus of theta plus, well, how can we actually describe again this double vector product as a matrix applied over R0 and then another matrix V tilde applied over the matrix V tilde which is applied over R0. I know it actually sounds like a joke, but it's like this. Are you with me on this? So this is V times R0, and this is V times R0, right? Oh, I was missing a 2. So here we have a 2, and then we have sinus squared of theta divided by 2. In fact, we can express this as a, sorry, we can express this as V times V over R over bar as a square, okay? Square applied over R0 over bar, okay? Instead of rewriting it like this, V applied over V, which acts over R0 over bar, we define a square matrices, which actually identifies this operation, okay? Yep.
So the direction of the second component will be along R0 over bar?
No. No, because
just because
yeah, I know what you're saying, but yeah, I know what your question is about. So we are always in a plane, which is the plane which contains this circumference, which is orthogonal to the axis of rotation. All right. So now we have A1 is something which is orthogonal to C P0. You see, it's like this. A1, A2 is something which as the direction of the radius. So it's P0C. But it's not parallel to R0 over bar. Okay? Okay. Is this what you were asking?
So I was asking that because we multiplied with matrices,
Mm-hmm.
the only component was R0 over bar in the final term.
Yeah?
But I understand that multiplying with that matrix is equivalent of cross products, so it also
Mm-hmm.
gives the direction.
Mm-hmm.
It also changes the direction.
Yes.
Just by changing.
Yes. Yes.
I understand.
Okay. All right. So, oops. So we just defined this new notation here. And so eventually we can do one thing right now. We can group the vector R0. So we can write R plus what? Something that, sorry, let me rewrite it a little more clear. Plus so this is R0. So we group R0. What do we have to write within these brackets? Well, first we have R0 itself. So we're going to have an identity matrix. Double under bar because we have, again, a matrix. Then we have what? We have this V tilde sinus of theta. Right? And then we have what? 2 V tilde squared sinus squared of theta divided by 2. Right? Cool. We call all of this within the matrix, within the brackets. This is a matrix, you see? It's a matrix which has the same dimension of R0. So R0 is a column vector which is 3 by 1 in the 3D space in general. So this has to be a 3 by 3 matrix. Acting on a 3 by 1 gives again a 3 by 1, of course, vector. So if we define this matrix A as this, then eventually you can write very elegantly P as what? R plus, as we said, R0 without an overbar initially, which is then equal to R plus A acting over R0 with an overbar. You see? With A, it depends only on what? On the vector V, because you remember that this matrix V tilde is basically built starting from the components of the unit vector V, which is the axis of rotation, and the rotation itself. So if we know the axis of rotation and the amount of the angle of rotation, we can write this matrix that when is applied over the position vector defined with respect to the local frame, it gives us the vector expressed directly in the inertial frame. Okay? This matrix A is called the transformation or rotation matrix, and this is called Rodriguez formula. So this is Rodriguez formula. And this is called, as we said, transformation or rotation matrix. It's actually quite elegant, no? A way of describing it. Okay. I would like to, so first a question. Do you prefer, I didn't know, I didn't remember if we go through this last time. Do you prefer to have a break and then start again or just have 2 lessons, one after the other, and we finish half an hour before, of course. And then there is a space for questions. What do you prefer to do? It's up to you guys. Do you want to continue or do you want to break? No shame in saying, if you're quite stressed by all this formulation, it's okay. No answer. Okay, let's continue then. And then we start, of course, before. We end before. All right, so just a final observation.
Professore, scusi. E la tilde va pure sulla A?
No.
No, quindi ho capito male.
No, la tilde è solo sulla B.
Quindi no, ho capito una notazione tipo le matrici doppio trattino basso e una tilde. Ho capito male.
Le matrici in generale hanno il doppio trattino sotto. Noi definiamo anche con una tilde superiore quelle matrici che vengono dalla semplificazione di un prodotto vettoriale. Sono matrici antisimmetriche. Quindi lei le vedrà praticamente soltanto su V e poi su poche altre cose. Ma in generale una matrice ha solo un doppio tratto sotto.
Ok, grazie.
Okay. So the last thing that I wanted to stress before actually having a small exercise is that in this writing that we wrote here for point P actually is valid for any point P within a body. Okay, and since we are having a course which is called multi-body dynamics, we will actually encompass system of more than one body. So eventually for a body I, we'll eventually denote this formula as with a subscript like this. So the position of a general point within the body I is the position of the origin of the frame I with respect to the inertial frame plus the matrix I, because of course every body will have its own rotation and orientation with respect to the inertial frame, right? Times R0 over bar I. Okay, I just basically added a subscript, okay? But this is somehow important from a conceptual point of view because it stresses out the dependence of these quantities with respect to each body. So each body will have its own A. Each body will have its position of the frame, of the origin of the local frame with respect to the inertial frame. And of course, each body will have the position with respect to this local frame. Okay? So if you want to just really have it in mind very clearly, so it's yeah, 1, 2, 3. This 1, 2, 3. X1, X2, X3. And then you will have, for example, one frame here for one body, and then another here, like this, for another body. Okay, so this is B1, B2, and B3. And so here you will have R1, okay? And then here you have, for example, R2. Okay, here you will have, actually, when we denote the axis, the subscript becomes a superscript, just to use the notation. So this will have B2, 2, or 1, actually, as we said. So the subscript indicates the type, or let's say, of the vector. The superscript indicates the body in this case. Okay. Actually, no, sorry. Let's have this consistent. Always subscript for the bodies. Okay. Everything up. Everything up. Okay. So let's not change top down, otherwise it becomes confusing. And so this is B2, 2. This is B1, 2, and this is like this. And each one of these local frames will have its own R and its own orientation matrix. Transformation matrix. All right, let's make a super quick exercise. Yeah.
Typical multi-body, how many reference frames would we define?
It depends on how complex the system is. We will actually have a seminar, and eventually at the end of the lesson, please remind me that I'll have to give you some info on the calendar regarding the seminars. So the seminars, as I said, are a cycle of 4 lectures held by represented by MSc using the software Adams. And you will see, I'm not sure if in the exercise that he will propose, but eventually, in general, that can be dozens and dozens of reference frames, even because these local frames are typically also used not only to indicate bodies, but also to indicate, let's say, markers or noteworthy points, or to help to describe a constraint. So there will be a lot. Okay. All right. So let's have an exercise. So in the 2D case, so let's consider a plane. Okay, so something which lives in the plane, x1, x2. All right. And let's imagine. So this is x1, this is x2. A body, which first has its local frame defined like this. Here, actually, I wouldn't confuse you saying that initially the local and inertial frame have to be always parallel. This is not a necessary condition, so I will correct this. I don't want to give you false informations. So then we have, for example, here B1, but of course they have to be orthogonal. All right. So this is the initial position. So this is at moment 1. And then at moment 2, they will undergo a rotation about an axis. What can be the axis in this case? This is a simple question, in fact. What can be the axis of rotation? It's a plane case, perpendicular to the board, right? So such that, for example, B1 goes up here. Again, for example, let's see it like this. And B2 goes like this, right? Again, here we will have our R, which goes like this. So, since, as I said, it's a rotation in the plane, the axis of rotation is perpendicular, right? So, in terms of components, how can we write it? Well, it will be 0, 0, 1, right? Okay. Then, if this is V, what's the skew matrix? What's the skew matrix like? Well, if you recall the definition, it's like something like 0 minus V3, 0, like this. Now, someone of you could comment, okay, but why it's not a 3 by 3 matrix? It should be. What are all the other components? The other components are trivial, they are all 0. So we will restrict the case for the sake of notation to the 2 by 2. Okay, that's all. But in fact, if we had to be precise, we would have to build a 3 times 3 matrix. But okay. So now let's implement Rodriguez formula and write our transformation matrix. So first we have V tilde. So we have 0, minus 1, 0, sorry, 1, 0. Okay? Then we have the same quantity, 0, minus 1, 1, 0, but multiplied by the sinus of theta, okay? The rotation that, let's say, so I'm not sure. Let's actually denote it like this. So typically, when we have a vector which goes out of the board, we define it as a point circled. Okay, so this is our V. Okay, it's just a matter of notation. So our V, the axis of rotation, is a unit vector which comes out of the board. It's perpendicular to the board. And typically, from a drawing point of view, in terms of notation, this is denoted as a point circled. While if it's going inside, it's actually something like this, typically. All right, so in this case, it goes out. And about this axis, we have, as we said, a rotation theta. So it undergoes a rotation theta about V. Okay? Now, we were in the process of writing the matrix A, following Rodriguez formula, and this is plus 2 times so it's this squared, but then again when we denoted this squared, we were actually again denoting the application of the matrix on itself. So we can rewrite it as we originally thought about it. Like this. So this
The first one is identity.
Yeah, it's the identity matrix, but nothing. You're correct. Thanks a lot. Yeah. Thanks a lot. So sin squared of theta divided by 2. Okay? If we do some math, very simple math, this can be rewritten as, again, the identity matrix plus 0 minus 1, 1, 0 applied over the sinus of theta plus 2 times, we just do the matrix product here between these 2 by 2 matrices, and we get minus 1, 0, 0, minus 1. And exploiting the trigonometric formula, this sinus squared of theta divided by 2 is basically, we already used this formula, is 1 minus cosinus of theta divided by 2. Okay? So now we have to just sum all of this. You can already see what it sums to. So 1/2 times 2 is 1. Multiplied by -1 is -1, and +1. So basically, this first term cancels out the identity matrix. So what is left is the sinus on the second diagonal with the minus on top, and then the opposite of the first, so the first diagonal with cosinus. All right. So let's continue. This becomes cosinus of theta minus sinus of theta, sinus of theta, cosinus of theta. Does this surprise you? No, right? That's the typical rotation matrix in the plane. So it works. We didn't cheat. Okay. So let's focus on one point that we actually have achieved. We said at the beginning, if you remember, that we needed 6 parameters to define completely the position, the general position of a body within a 3D space. 3 coordinates, 3 parameters, are basically due to describe the translation. Okay, so they are the coordinates of the vector capital R. So parameters to define the position and orientation of a body in the 3D space. So we have R, 3 parameters, but then we have A, right? Because we have to know A in order to be able to orient correctly one body within the 3D space. But A, as we said, is a function of the axis of rotation and of an angle. So the question arises, do we actually have 4 parameters? Needed to define the orientation, so it would amount to 7. It actually doesn't really add up. What's the trick? Because we said that they have to be 6, and in fact they are 6, but here we have 7.
The magnitude of unit vector component.
Correct. This is a unit vector, so we have 7 parameters, but only 6 are independent, because we have to enforce the V, so V1, V2, and V3, the components of V, they have to give rise to a unit vector. So in this case, we have 7 parameters plus one scalar constraint. So we can actually say that in general we need 6 independent parameters to completely and univocally define the position and orientation of a body within the space.
Don't you also need R0 over bar?
Yes, but this is actually not true. because we need R0 over bar if we want to locate a position of the body. But if we want only to know what is the position and orientation of the body itself, this can be done being able to identify and to define its frame, the local frame, right? If we know the local frame, we know the position and the orientation of the body itself as a whole. Then, as you said correctly, if we want to exactly know the position of a point, we need to know what is first the position of this point with respect to the local frame. So that we have called R0 over bar. And then apply A and all the other thing to be able to reconstruct its position in the inertial frame, right? But in general, if we know R and A, we know the position and the orientation of the local frame, and that's enough. So 6 independent parameters. 6 independent parameters are needed to identify univocally the position and orientation of a body within a rigid body within the 3D space. Now, let's adapt a final consideration. How many ways are there to express these parameters that we need to identify the position and orientation of a body? Multiple ways. We will actually describe 3, actually 4 if we have time. First of them is Euler's parameters. So this is the way we parameterize rotation and translation of bodies using set of parameters. There are different ways of describing this set. We always refer to the angle of the orientation and the axis of orientation, okay? So here we will actually focus on the parameters needed to describe the rotation, okay? For the translation, well, there is not much fun to have. It's always the components of R capital, okay? It's R1, R2, R3, and that's it. But for the orientation, we can have a little bit more, let's say, liberty. Euler's parameters. Please note that this is something different from Euler's angles that we will discuss probably next lecture. So Euler's parameter is something, Euler's angles are different. Have you ever heard of them? Hope so. All right. Euler's parameters are defined like this. First of all, they are 4. And they are defined like this. Theta 0 is equal to cosinus of theta divided by 2, where theta is the angle of rotation. Okay? Then we have theta 1, which is defined as V1, which is the first component of the axis of the unit vector defined the axis of rotation, times the sinus of theta squared. Then we have theta 2, which is V2 defined times the sinus of theta divided by 2. And then we have theta 3, which is V3 times sinus of theta divided by 2. Why? So first consideration, they are 4. So 4 parameters to define the orientation. We already know that something is actually, this is more than we should need eventually. We would expect something like 3 parameters. So it means that, of course, they are associated with a condition, with a constraint, which actually makes us understand why they are defined like this. So this is basically just a rearrangement of the components of the unit vector plus the angle of rotation. It's nothing really fancy. But why really this way? Why was this rearrangement done like this? Because if you define theta with an underbar, so the vector, as theta 0, theta 1, theta 2, theta 3. So it's a column vector, it's 4 by 1 column vector. You can enforce the fact that v1, v2, and v3 have to be components of a unit vector in a very simple way. Right? If you try to express theta, the vector theta, like this, and you basically, if this is a, you can actually, for those of you who didn't actually notice, this is exactly equivalent of writing theta scalar theta equal to 1. So if this is a matrix operation, this is a scalar operation. So this is a scalar product, this is a matrix product. The result is the same. If you do it, you actually see that it actually holds. In fact, if you do the square of these components, you have cosine squared, this square, this square, this square. You group sine squared, and so you have v1, v2, and v3 squared all together. So it's 1, the sum. So eventually you end up having cosinus of squared of theta divided by 2 plus sine squared of theta divided by 2. And so that must be 1. Okay? So that's why they were defined like this. One way of actually reusing these parameters is through the definition of quaternions. Have you ever heard of quaternions? Right. So this is basically the same thing. Okay? Quaternions is a set of quantities in the 4th dimension, like this. So for example, you can identify the quaternions as a quadruplet like this. Cool. So it's a vector which lives in the 4-dimensional space, just like theta. And it's defined like this. Theta 0, which is a scalar, plus theta 1 multiplied by a unit vector I, plus theta 2 multiplied by a vector j, plus theta 3 multiplied by a unit vector k, where basically if you see the base vectors of our space where the quaternions live are defined by 1, so the scalar number 1, I, j, and k. These are the base vectors. This is a vector of course, a scalar, which define the space of quaternions. And this basically relates the quaternions to the Euler's parameters. And as you already know, we will not go into detail with this, but there are relationships which hold when you, for example, consider a succession of rotations, which we will study later on, but not with quaternions, which relate, for example, when you have the multiplication of I with j or I with k. Okay, for example, you have that I multiplied by I is 1, so it's a scalar. Then if you have I times j times k, so it's a number of permutation. You can have either plus 1 or plus or minus 1 or plus I or minus I. So basically you have plus or minus one of the other base vectors. So they are orthogonal basically. But that's all basically. So talking about Euler's parameters and quaternion is almost the same thing. Why is it actually also nice, to write down Euler's parameters? Why are they so useful? First of all, and this is the real advantage. So we paid in terms of numbers of parameters because we have more than necessary, because we have 4 instead of 3. But the advantage of using Euler's parameters is that they have no problems of singularity. Okay. Okay, so there is no configuration, no orientation in this case, because we are always parameterizing a rotation here, that cannot be described with this set of Euler's parameters. This is not going to be the case for other parameterization that we will see. For example, Rodriguez parameters or Euler's parameters. Have you ever heard of the gimbal lock problem? We will see that. It's actually something that happened in real life for, what was that, Apollo? Can't remember the number. So they actually had an issue because the orientation of the spacecraft was done using Euler's parameters. And we will see that with this set of parameters, you can actually end up in a configuration in which you will not be able to describe anymore any kind of rotation, so any kind of orientation of your spacecraft, of your body. And so they had issues for that. But we'll see this later on in detail in next lectures. Last 7 minutes, I would like to help you out in describing the orientation, the transformation matrix using Euler's parameters. So we'll let you see this right now, and then I will never ask this again. No, I'm joking, just because it's something to let you see how it's actually composed, but then I will never ask you at the exam to learn by heart this, okay? But it's, I think it's useful to see its structure at least one time. So again, it's a 3x3 matrix. So this is the first component, so the first element actually. And actually, this gives you already the impression and information which is relevant, because you already see from what I'm actually writing that the dependence of this transformation matrix from Euler's parameters is highly nonlinear. You see, because this is nonlinear when you have this multiplication. There are squares and so on. And we will see that nonlinearities is actually one of the great issues of multibody dynamics. Nonlinearities due to the presence of these terms, which we cannot linearize, because in general, this is an important point, we will stress it out often during the course, but you cannot go into a linearization, which is typically the approach used in dynamics so far. Why? Because when you deal with rigid body rotation, because the real deal is the rotation, and also the translation, but that's another point, you can, in general, you have to be able to encompass large rotations of more and more degrees. And if the angle of rotation is big, you cannot linearize it. You cannot confuse the sinus with the angle. You cannot say that the cosinus of theta is 1, right? And so this follows. Okay. All right, let's moving. And we will see that also this matrix has properties, interesting properties. We will investigate them next time. Last 3. This is very annoying, but at least one time we have to go through this. Okay, that's it. So again, this we can say that A is actually highly non-linear in the thetas, right? So we can in the components of the Euler's parameters, it's actually highly nonlinear. Last thing, and then you're free to go, is that we can rewrite A as a product between two matrices, which we will use later on. And these matrices are the following. A can be written as H, the matrix H, applied over H over bar transposed. Where we have that H is again a 3 by 3 matrices, but in this case it's written like this: minus theta 1, theta 0. No, sorry, it's not a 3 by 3, of course, it's a 3 by 4 matrix. Minus theta 3, theta 2, minus theta 2. Again, I won't be asking you the composition of these matrices at the exam, but still, it's again nice to see it once, because this matrix H and then H over bar that we will see now, they are linear, you see, in theta. So we can, the useful thing about this reformulation of H is that we can write a nonlinear relationship between A and the Euler's parameters as, let's say, a composition of linear matrices, okay? And this is very similar, so similar that you won't be exempted from mistaking the one for the other, but they are in fact a little bit different. Again, also this one is linear. Okay. So, I think that's all for today's. Next time, which is tomorrow, we will go through more parametrizations. We will go through Euler's angles. We will see what I've already anticipated. So the gimbal lock. We will see Rodriguez parameters. Also the direction cosines, force, maybe, if we have time. And then we will investigate some properties of the rotation matrix. We see that it's an orthogonal matrix, that it has some other nice properties that we will use. And then eventually, maybe not tomorrow, but next week, we will see how to describe successive rotations, okay? Because many times a body undergoes not just a simple rotation, but a series of rotations. So how can we describe this? We will see that there are basically two approaches, which are called single frame and multi-frame rotation methods, okay? But this is matter for probably next week. Any question? Good. Anything from home? Guys, are you there?
Nessuna
Sì,
domanda.
no.
Okay, so this basically closes today's lecture then.
Arrivederci.
Arrivederci.
Arrivederci.